So as I was saying, if you look back at our last lecture, we started talking about the sampling distribution of the sample mean. And at the very end of the lecture, like if I load it up, give it a second, it takes forever to. I did this example, or I started talking about something called the central limit theorem. And then I did this example talking about baseball player salaries. Does this kind of ring a bell to people a little bit at all? I know it's been a week, right? And like a lot's gone on in the last couple of days, so it's easy to forget. So I'm actually going to pick up there to start class. One other thing, a little scatterbrain today. Have this chart handy with you. If you don't know where it is, it's under the week 9 tab in the course content. We're going to use it once today. And then how many people have their graphing calculators with them today? Okay, I hope that you do. We're going to use our graphing calculators a lot today. Okay, so basically what I'm going to do is the first example we're going to do, I'm going to show you how to do by hand. And then after that, we're just going to use the graphing calculator. Okay, so one other announcement, if you remember, our next exam was supposed to be next Thursday, the 12th, but I'm moving it to Tuesday, the 17th, okay? So next Tuesday, the 10th, I'll post your next homework assignment. We'll actually kind of start something new on the 10th and 12th, but I'll spend the second half of class on the 12th just reviewing for you, okay? Does anybody have any questions about any of that before I get started? Any questions in general? No questions? Okay. Come on, PowerPoint. Sorry, my PowerPoint's acting up. Can you guys hear me okay?
Yes.
Yeah, I'm sorry, my PowerPoint's freezing. Let me restart my PowerPoint. Sorry, my PowerPoint kind of freezing there. All right, much better, much better. Okay. So today we're going to pick up talking about sampling distributions. Okay, so this is from last class here, all right, what we were talking about. All right, so I'm just going to do the highlights of this for us. Okay, so this is talking about the mean and standard deviation of the sampling distribution of X bar. So here's what we know about X bar. Okay, it's going to be a random variable going forward. All right, and this is because its value changes from sample to sample. All right, so suppose that a simple random sample of size n, so, we're going to sample 30, 40, 50, how many ever people, is drawn from a large population that has mean mu and standard deviation sigma, okay? The sampling distribution of X bar will have mean, will denote as mu sub X bar, and it's just equal to whatever the population mean is. And its standard deviation we denote as sigma X bar. And this is the most important thing for today's class, okay? You take the population standard deviation and you divide it by the square root of the sample size, okay? Basically, just to give like a kind of a hint for all the problems we're gonna do today, all the problems are done exactly how we were doing them last week. It's just like we have this extra step. You just gotta take the population standard deviation, divide it by the square root of it. Okay, we also call this standard deviation, it's also referred to as the standard error. Okay, so keep these two formulas handy today, all right? Or keep them in the back of your mind. Is everybody okay if I move on? Okay. So then we ended class talking about this thing here, okay? Central limit theorem. And it went like this. So these are some key points. If your original variable x is normally distributed, the sampling distribution of x bar will be normal. Okay, and that's regardless of the other sample size. All right, but then what if your population is not normally distributed? So it turns out we have this thing called a central limit theorem. It's like the most important theorem of the class, okay? And it just goes like this. The shape of the distribution of the sample mean becomes approximately normal, so it becomes this normal distribution as the sample size n increases, and this is regardless of the shape of the population. And the key important thing is, as long as the sample size is greater than or equal to 30, the sampling distribution of x bar will be normal. Okay, and then last class a week ago, geez, a week ago, it's crazy how quickly time flies. Or actually, I don't know, actually a week ago seems like forever ago, I take that back. I think I did the example where I showed with baseball player salaries that if we did sample sizes of 30, the distribution of those X bars will be normal, right? And so now we're kind of caught up to where we were last class. Is it kind of coming back a little bit? Remember me talking about this? Okay. I got one, yeah, kind of. Okay, good. All right, so let's do some examples of how we're going to use this. And this stuff will be on your next homework and on your next exam. And speaking of your homeworks, I will grade your homeworks that you just submitted on Tuesday. I'll have those in for you on Friday sometime. Okay. So here, I've got two examples picked out for us, okay? And it goes like this. Suppose that the mean time, here's the first one, for an oil change at a place that's referred to as a 10-minute oil change joint is actually 11 minutes, okay? So at this place, what we're told is that the average time, mu, is 11.4 minutes. Does it really seem like a 10-minute oil change joint? Like, not really, right? Because you're on average, you're waiting 11 minutes, but we won't nitpick them. And it says a standard deviation for the time that you have to wait for your oil change is 3.2 minutes. Okay. So here's what we're doing. If a random sample of 35 oil changes is selected, okay, so we're going to randomly sample 35 people who got an oil change, okay, and basically what we're going to ask them is, hey, how long did your oil change take? How long did your oil change take, okay? So we're going to sample 35 oil changes. And basically what we're going to do is we're going to compute the mean oil change time. Okay. So the next thing it says is describe the sampling distribution of this sample mean. All right, so let me ask you all this question, and like you can turn your mic on or you can post in chat. If I sample 35 people and ask them how long it took to get their oil change, and then I sampled another 35 people and I asked them how long it took for them to get their oil change, Do you think the two means would be exactly the same?
No.
No, they wouldn't, right? Like it'd be different from sample to sample, okay? But so what I want to do is if I realize they're going to be different and I were to repeat this experiment over and over and over and over and over again, like what would the distribution of a bunch of sample means look like? Okay, so how do you begin to answer this? What's the sample size I said you're taking here?
35.
Okay, yep. So because the sample size is greater than 30, okay, and I'll even put in parentheses, it's 35, okay? What did I say was the most important theorem of the class? Go back. Yes, right here, the central limit theorem. Okay, most important in class, okay? And look, this is what it's saying. As long as the sample size is greater than or equal to 30, which it is, right, the sampling distribution of X bar will be normally distributed. So this is what we're able to say. Because the sample size is greater than 30, the sampling distribution of X bar will be normally distributed with, so when something is normally distributed, okay, you want to describe what its mean and standard deviation is. So I'm just going to go back for 1 second here. This right here tells you what the mean and standard deviation is. All right, so it's with mean, which we denote as mu sub X bar, okay? So it's the average of the averages, okay? And the average of the averages is going to be equal to the average, mu. So what is the average time for an oil change at this place? No, yep, 11.4, right? It says it up here. The mean time is 11.4. And now we can find the standard deviation, which I'll call the standard error. That's equal to sigma X bar. And the formula is you just take the population standard deviation and you divide it by the square root of n. Okay, so you're going to take the standard deviation here that was given to you is 3.2, and we're going to divide it by the square root of 35. So let's grab a trusty calculator here. So I'm going to take 3.2 divide by the square root of 35. I'm going to get this. Did anybody else get this? Yeah. Great. Just like to have my work checked a little bit, you know.
Professor, just a question. Where did you get the 3.2 from?
Where did I get the 3.2 from?
Yeah.
Notice how right here it's given.
Got it.
Do you see it?
Yes.
Okay. So this is important. You're going to want to take this out at least 4 decimal places. So 0.540, and I'll round it to 9. 0.5409. Okay. So that's what this part is. Look, I told you it's normally distributed now, and then I gave you the mean and standard deviation. So remember, standard error is just another way of saying standard deviation. All right, so now I'm going to ask you a probability question. And like, if you remember, was your homework just a bunch of probability questions related to the normal distribution? Yeah, it totally was. Okay, so this one is going to be just sounding a little different. Okay. So if a random sample of n is equal to 35 oil changes selected, what is the probability the mean? So the mean. So what this means is the X bar that you get, all right, the mean oil change time is less than 10 minutes. Okay. So here's what I'm going to do. I'm going to define a variable. Okay. I'm going to let X bar be equal to the mean oil change time in a sample of 35 oil changes. All right, and I want to find the probability the mean is less than 10 minutes. So I want to find the probability that X bar is less than 10. Okay. Does this look kind of like the previous problems we're doing? Just the only difference is I have an X bar instead of an X there. Yeah, okay. Does anybody remember what I said really helps that you do next? I know it was a week ago. Yeah, the sketch. Okay,
Practice.
So exactly. Yeah, what am I going to sketch is the next question. So I'm going to sketch the sampling distribution of X bar. Okay, and here's what I know. Boom, normally distributed. So I'm going to draw the bell curve. It should be centered at 11.4. And I want it to be less than 10. So 10 is over here. And am I going to shade to the left or to the right if I want to be less than 10? Yep, perfect, perfect. So I'm going to show you this one time how to do this by hand now, okay? Does anybody, so we spent a lot of time with the calculator, okay? But does anybody remember when we were doing this by hand? When I say by hand, what I mean is we're going to use this table right here. So to use this table right here, does anybody remember what I have to calculate? It started with a Z. Yep. Thank you, Emmanuel. Yep. I have to calculate a Z score. Okay. So the formula for a Z score is it's equal to the variable minus the mean divided by the standard deviation. Well, in this case, this is my variable, X bar. The mean is this right here, mu sub X bar. And the standard deviation is this right here, sigma X bar. Okay, that's why we found them. That's why we went through the process of writing them out in the step above, okay? So this is 10 minus 11.4 divided by, now this is one of the most common errors I see. This is the standard deviation now, okay, of the distribution of X bar. So it's divided by 0.5409. So don't use the original standard deviation, okay? Let's grab that trusty calculator. Never lets you down. So you're going to take 10. I'll do this all in one step in my calculator. If you're going to do it in one step, you have to put the top in parentheses. So 10 minus 11.4 divided by 0.5409. Did anybody get this number if they did it with me, just out of curiosity?
Yes.
Awesome. And if you're going to use Z-scores, do you remember how many decimal places you have to round it to?
4 places?
Not 4. Z-scores, yep, perfect in the chat there. Yeah, the Z-scores, we actually go to 2 decimal places. So it's negative 2.59 when I round it. Negative 2.59. So this problem now just becomes, hey, what's the probability a Z-score is less than negative 2.59? So that's when we grab this table. And to read Z-scores, right? The first 2 digits are minus 2.5. So you go to here, minus 2.5. And the last digit is a 9. So do you get, thank you. Yep. It's 0.0048. And that's our answer. Woo, not too bad. So does this process kind of ring a bell? Like we were doing this a lot last week.
Yep.
Yeah. So do you notice literally like just computationally, okay? So if you're computationally, the only thing that's different is this part right here, okay? That you're gonna divide the standard deviation divided by the square root of the sample size. That's like the only thing that's computationally different, okay? Otherwise, it's the same process. But then I think I said it can actually be a little bit easier if you guys use your calculator. And then we did a bunch of problems with our calculator next. So let me ask you 2 follow-up questions to this, and we'll go back to using our calculator, okay? Is everybody okay if I move on? I got 1 yes. Okay. All right, so the next question, okay. If a random sample of n is equal to 35 oil changes selected, what is the probability the mean oil change time is greater than 12 minutes, okay? So it's the probability the mean, okay, is greater than 12 minutes. So it's the probability that that X bar you get is greater than 12. I know it seems silly. What do I suggest you draw next or do next? Sketch it. Sketch it. So I'm going to sketch the distribution of the sample mean. Should be centered at the mean. Which is 11.4, and I want to be greater than 12. So am I going to shade to the left or to the right? To the right. And you guys are getting the full sound effects today. I hope that's okay. All right. So at this point now, I think it's actually easier to use your calculator. Does anybody remember what the command was called in your TI-84 calculator of awesomeness? Yep, we're going to use distribution, and then what under that?
CDF.
Yep, thanks. Okay. So it's the normal CDF in your calculator, which involves inputting 4 things. The first thing you have to input is the lower value, okay? So going across this as a number line, the starting lower value of the area you're looking for is 12, comma. The next thing you're going to put in is upper, yeah. And since it's a tail area to the right, does anybody remember what you have to put in? Yep. The next thing you put in then is the mean. What was the mean here of the sampling distribution of X bar? Yep. And then the next thing you're going to put in is the standard deviation. What number am I going to put in there though? Yes, perfect in the chat. Thank you so much. Yeah, you don't use this, okay? You're gonna always use sigma divided by the square root of n. So whenever you see a problem that says, hey, what's the probability the mean is greater than or mean is less than, that's the key indicator to use this. So let's grab that. I'm just gonna do it in the TI-83 here first. I like to go old school. So it's second function distribution, normal CDF, so 12, comma 9999, comma 11.4, comma 0.5409er. Did anybody get this when they were doing it by hand, just out of curiosity, or doing it on their own with the calculator? 0.1337 when I round it. Perfect, perfect. All right, so what's easier, calculator or no calculator? I mean, calculator or doing it by hand this way? Yeah,
Professor, can you please repeat why you're not using the mean? I mean, I'm sorry, the standard deviation in the last number?
Yeah, so because we're now talking about the probability of the mean, okay? So whenever you see the word mean, okay, and you have this instead of X, you're always gonna need to use this sigma divided by the square root of n. Okay, like I'll give you a hint, like whenever you get, whenever you see a problem like on the next exam or your next homework, and it says something like, if a random sample of size 20 is taken, and what's the probability the mean is greater than this number? That, you know, when I give you like a sample size and you see the word probability the mean or probability the sample mean, then you're gonna need to use this standard error. Does that help a little? So n is the sample size and sigma is the original population standard deviation. So like if you look back here, when we started the problem, sigma was the given standard deviation of the population and n is the sample size. Does that make it a little bit clear, Leonardo? Okay. And don't worry, we're gonna work another example right after this, okay? All right, so let's do this next one here. If a random sample of n is equal to 35 oil change is selected, what is the probability the mean oil change is between 10 and 12 minutes? So it's the probability the mean is between 10 and 12. All right, so again, what we're gonna do is we're gonna sketch the distribution of the sample mean. Should be at 11.4 is the mean, and I want to be between 10 and 12. Okay, so I'm going to shade between them. Okay, so let's use our calculator again. It's going to be the normal CDF command. Help me out here. What's my lower value?
$10,
Yep. What's my upper?
$12,
Yep. And the mean is 11.4. And what value am I going to put in for the standard deviation? Yep. So I'll plug it in the TI-84 this time. So second function distribution, normal CDF, it's going to be 10 to 12 to 11.4 to 0.5409er. Yep. How many people, if you did it in your calculator, got this right here? Awesome. Okay, so it's 0.8615. Not too bad?
I have a question.
Sure.
For the standard deviation, we always have to use a 0.54095.
This right here, 0.5409.
Yeah.
Yeah, if the problem mentions a mean, yes. Okay, if it doesn't, like the homework didn't, then you would use the original value.
Wait, you said if the problem states what?
Like if it says, what's the probability of the mean oil change? Like,
The meme, okay.
yeah, that's how you'll know you'll need to use this sigma over the square root of n.
Okay, thank you.
Yeah.
So, Professor, in this case, you're not using the upper number, the 999 anymore?
Nope, because it's a between, like between 10 and 12, the lower value of the area you're looking for is 10 and the upper is 12. So you only use the 99999 stuff when it's a right-tailed like this. And then if it's a left-tailed like this, you would use the negative 99999. We're going to do another example. We're just going to stick with the calculator. So you'll see it again, okay? You guys ready for another one? Okay. Anybody else? Everybody else good if I move on? Another example will help make this, have this make sense. All right, I'm going to move on. So I picked this one, great, because I had a kid recently. But so this is interesting, I thought. The length of human pregnancies is approximately normally distributed. Okay, so they're telling you right off the bat that pregnancies, all right, not, obviously, not every pregnancy lasts the same, right? But the length of human pregnancies follows this bell curve shape, normally distributed, with a mean of 266 days, and they tell you the standard deviation is 16 days. Okay. All right, so here's the first question. What is the probability that a random sample of 16 pregnancies has a mean length greater than 270 days? Okay. So this is weird, okay? Can anybody tell me, like, what's the giveaway in this that I'm gonna need to use this formula here, this sigma divided by the square root of n?
The normally distributed part.
That doesn't, okay, first off, it's a sample size of 16, and then it asks you the probability that a mean, okay? So here's how you're gonna have to tackle this problem, okay? First off, they're asking the probability that a mean length is greater than 270 days. So I'm gonna define a variable. I'm gonna let x bar be equal to the mean length of 16 pregnancies, all right? And I want to find the probability that that mean length, this random variable x bar, is greater than 270. Okay, so now here's the thing. To be able to answer this, okay, you have to describe the sampling distribution of X bar. So what is the sampling distribution of X bar? So here's the deal. Like, what did I say the magic sample size number was? Like, you had to be greater than what number? Okay, yeah, yep, had to be greater than 30, yep. Do I have greater than 30 pregnancies here? No, I only have 16. Okay, no big deal, no big deal. But so there was a little caveat here. Let me go back a few slides. If the original variable, so if pregnancies is normally distributed, which we're told it is, then the sampling distribution of X bar is normally distributed. So it doesn't matter in this case that you don't have 30. You can just say something like this. Because the lengths of pregnancies are normally distributed, the sampling distribution of X bar will be normally distributed with. So when something's normally distributed, what two numbers do I want to calculate next? The mean, which we denote as mu sub X bar. Yep, thank you, Dulesky. Yep. That's equal to the population mean, which is 266. And the standard deviation, what's the formula for that again? Sigma divided by the square root of n. So it's 16 divided by the square root of 16. Does anybody know what that's going to be? They can even do it in their head. I think it's 4, right? Because the square root of 16 is 4. And then 16 divided by 4 is 4. Does that make sense? Did I do that right?
Yes.
Thank you. Woo, simple math. Yes, I got it. Okay, so now we can actually answer the question. We know it's normally distributed. I asked you for this probability. So I sketch it. Should be centered at 266. And I want to be greater than 270. So I'm going to shade to the right. Like that. So once you have it set up like this, is it pretty straightforward then? Well, like what you should do next with the calculator? Like it's not too bad, right? So we'll go normal CDF. What's my lower value here? I think it's 270, yep. And because it's a tail area to the right, what do I need to do? Yep, 99999. The mean is 266. And am I going to put 16 or am I going to put, yep, thank you. Yep, I'm going to put 4 for the standard deviation. So let's grab this. I'll do it on the TI-83. So second function distribution, normal CDF, 270, comma, 99999. comma 266, comma 4. If you were following along and did it on your calculator, did you get that number? 0.1587 when I round it. Awesome. .1587. Boom. Not too bad. Are
Will
you
there
kind
ever be a scenario where the question doesn't state that it's normally distributed and the sample size is not greater than 30?
That's a fantastic question. And no, because the reason I would never give you a question like that is because then you couldn't use these methods I'm talking about.
So is
So
there another method that
to handle that, no, you can't. You can't. Not in a statistics 101 course
okay.
or 140 course. Sorry. But at least in terms of this class, I'll never give you a question you can't answer. All right, let's try this next one here. There's a subtle difference in this one, okay? What is the probability that a random sample of 20 pregnancies has a mean length greater than 270? What's the subtle difference in this problem? How many pregnancies are we now? Yeah, the n changes, okay? So we have a new variable, right? So I'm gonna let x bar be equal to the mean length of 20 pregnancies. And let's describe the sampling distribution of this new x bar, because it's not 16 pregnancies, it's 20. And then it's just the same thing, again, because the lengths of pregnancies are normally distributed. The sampling distribution of x bar will be normally distributed. With, is this going to change? Use of x bar, does that change? It's still equal to the population mean, so no, yep, it's still equal to 266. But will my standard deviation change now, my standard error? Yeah, sample size changes. Yeah, that's a good change. So it's going to be 16 divided by the square root of 20 now. And this one, you're going to have to remember to go out 4 decimal places. It's 3.5777 when I round it. So now I can answer the question, okay? What's the probability that this new x bar is greater than 270? Well, again, just go normal CDF. Oh, what did I forget to do that really helps? Sketch, but it's actually the same sketch as up here, okay? So my lower is going to be 270. My upper is going to be 99999. My mean is going to be this right here, 266. But what value am I going to put in for the standard deviation? Yep. 3 point, that's okay. Yeah, it's this value that you compute over here, 3.5777. I'll do it in the TI-84 here. And you should get, I think, oh my gosh, I made it a little, put an extra 2 in there. I'm the worst, I'm sorry. How many people got this right here? 0.1318, yeah. Yeah, sorry about the little typo there. And that's your answer. So notice when you increase the sample size, the probability got smaller, which makes sense, right? Because if you increase your sample size, we all make mistakes. Trust me, I make a lot of mistakes daily. If we increase our sample size, our statistics get better and better and better. So the probability that we stay that far out, greater than 270, should definitely shrink. Okay, not too bad. All right. Let's just answer 2 last quick questions and then we'll take our break. So we're going to stick with the sample size of 20. So remember these numbers here, okay? What is the probability that a random, and I'm sorry, everybody okay if I go on? Everybody okay? Okay. What is the probability that a random sample of 20 pregnancies has a mean length less than 260 days? So here it's just the probability that that mean, X bar, is less than 260. Well, you should be at 266. I want to be less than 260. I'm now shade to the left. So I'm going to use my normal CDF. What's my lower value here for this? Because it's a left tail test. Yep, negative 9999. What's my upper? Yep. My mean and standard deviation are going to come from right here. Okay, because it was a sample of 20. So it's 266, 3.5777. I'll do it on the TI-83 here. So normal CDF, negative 99999, comma 260, comma 266, comma 3.5777. How many people got that number if you did it in your calculator? So 0.0468. Okay, yeah, so I think I did it right. 0.0468. Not too bad. All right, now let's do this last one and then we'll take our break. Okay, so what is the probability that a random sample of 20 pregnancies, again, has a mean length between 258 and 272? So it's between 258 and 272. So again, I'm going to sketch the curve. should be at 266. I want to be between 258 and 272. So it's normal CDF. What's my lower here? Yep. What's my upper? Yep. Thank you. And then my mean stays the same as 266. My standard error, standard deviation was 3.5777. So in the TI-84 here, just so you can see the difference, is 258, 272, 266, 3.5777. And you should get this, 0.9406 when I round it. Anybody else get that just to verify? Awesome, 0.94. And I appreciate the help in the chat there. 0.9406. All right. Yeah, I think you guys can handle one of these on the, maybe two of them on the exam. I got one, yeah. Another, yeah. Another, yes, great. All right. Whew. What do you think we take a 10-minute break? We'll start back at, let's start back. Yeah, I'll post a practice test, and also like the homework that I'm going to assign is basically going to be a practice test for you. The next homework that I'm going to post on Tuesday. Yeah, yeah. Is the baby okay? Yeah, that's a great question. Yeah, he actually he woke up from a nap before class started, so my wife took him on a walk. But he came home, so I don't know why he's not crying. That's a good question. I'm gonna go check. All right, so we'll start back. We'll come back at around 2:03, 2:04. Okay. So I'll be back in 10 minutes, everybody. 2:03 or 2:04. All right, can everybody hear me okay?
Yes.
All right, thanks. I guess we'll get started again. All right. So I want to spend the next 40 minutes or so talking about a new statistic and a new sampling distribution. Okay, so this is called the sampling distribution of the sample proportion. So this concept of a proportion, I mean, we've all heard that word before, right? Like we have some kind of understanding or concept of what a proportion is. So let me put a formal definition to that and show an example or two of it. Okay, so suppose that a random sample of size n, so again, like, you know, in this case, it'll be 100, 200, 300, 1,000, whatever, is obtained from a population in which each individual does or does not have a certain characteristic. Okay, so there's only two, you either have this characteristic or you do not have this characteristic. Okay, like, you know, either you voted on Tuesday or you did not vote on Tuesday. That's what I mean by you do or do not have this characteristic. Okay, the sample proportion, okay, which is denoted as P, and it got cut off a little bit here, but it's P with a little caret sign on top of it. Okay, and I love statisticians, like, you know, when they had X with bar over it. Oh, let's just call it X bar. So what do we call this? P with a little hat on top of it. It's actually called P hat. Okay, that's not a joke. That's what it's called. Okay, is given by. So you want to find the sample proportion of individuals who have this certain characteristic. Okay, so sample proportion of individuals who have a certain characteristic. Okay, is just given by, you take the number of people in the sample who have that characteristic, X, and you divide it by N, the sample size. Okay, so X, as I said, is the number of individuals who have that specified characteristic. And this P hat is a statistic that estimates the population proportion. So P hat estimates the population proportion. All right, and the population proportion is just given as P. Okay, so when you see P with the hat over it, it's the sample proportion. When you see P just by itself, okay, that's going to represent the population proportion. Okay. If everybody, okay, if I go next slide and show you an example of this. All right, and so, you know, yeah. Go ahead, I'm sorry. Were you okay? Okay.
Yeah.
All right. So some of the examples I have picked out in the next couple slides are political in nature, but I do not want to talk politics at all. Okay. I've actually only talked politics for the last 2 days, and I'm just so sick of it. I don't know if anybody else has felt that way. But I just want to, thank you for the laugh. Yeah. Don't ever want to talk about it again for another 4 years. Yeah. Also, just know some of the numbers are just made up. Okay, so if you have a specific political leaning or whatever, these numbers were just made up. Okay, so don't be like, well, I don't think that's true. You know, just totally made up numbers. Don't ever want to talk politics. All right, so here's just a silly example. Okay, in a Quinnipiac University poll. So Quinnipiac University has a real survey research department, and they conduct polls all the time. Okay, this was conducted in May of 1,745 registered voters. Okay, so this right here is my sample size. Okay, nationwide, and they were asked whether they approved of the way the president is handling the economy. Okay, so the question was approve. and you only have two characteristics. It's either yes, you approve it, or you do not approve, so no. Okay, so you either have the characteristic of yes, you approve, or the characteristic that, or the opposite of it, that you don't. 349 responded yes. Okay, so that's my X. That's the number of people who said, yeah, doing a great job. So obtain a point estimate. So this point estimate is a single value statistic. Okay, in this case, the point estimate, the single value statistic for the proportion of registered voters who approve of the way the president handling the economy is P hat. Okay, so we want to find P hat. So if I want to find the sample proportion, I would take what and divide it by what? Well, if you look back here, you're going to take the number. Yep, thank you. It's just X divided by N. So you would take the 349 people who said yes, you divide it by the total. And I actually have this on the next slide. You will see that you'll get 20%, 0.02, okay? So is at least calculating a p hat, very, very straightforward. Straightforward, yay or nay? Yeah, I think so. Yeah. Okay. So I want to walk you through an experiment here, okay? And what I want to do is I'm going to use like simulation, and I'm going to create some histograms to show you something to describe the distribution of the sample proportion, okay? So our goal here is describe the sampling distribution of the sample proportion. All right. So according to a time poll conducted in June, okay, 42% of registered voters plan to vote in the upcoming election. Okay, so this is totally made up. Okay, just so you know, like oh God, I definitely want to talk politics, but like the real value at this last election was closer to 75% of registered voters voted, which is like unheard of. But so according to a time poll conducted in June, 42% of registered voters plan to vote in the upcoming election. So let's just assume that this number is the actual P. Okay, that it's actually 0.42, okay? So what I want to do is I want to describe the sampling distribution of the sample proportion for 3 different sizes, okay? So I want to describe it for what we call 10 people and ask them, hey, are you going to plan to vote in the upcoming election? And then I'm going to do the problem where I call 50 people and I say, hey, are you going to vote in the upcoming election? And I'm going to call 100 people, okay? But I'm going to do this like 300 times, okay? So what I mean by that is this, okay? So for sample size 10, okay? Sample 1. I'm going to call 10 people and I'm going to compute a p hat for that, okay? And then I'm going to do this 300 times, okay? Okay. And here's what I'm going to have, all right? I'm going to have 300 different p hats, okay? 300 different p hats. Now, is every single sample proportion going to be exactly the same? Some will be the same, but will there be some variation in them? Yeah, it's just like sample to sample. It's going to be different, right? So then I'm going to repeat this experiment. I'm going to do this again. For n is equal to 50. So instead of calling 10 people, I'm going to be like, well, wait a second. Let me just call 50 people in each sample. So for sample 1, I'm going to compute a p hat for that. And I'm going to do this 300 times. Okay? So again, I'm going to have 300 different p hats. Okay? And then I'm finally going to do this for 100. Okay, I'm going to call 100 people. I'm going to say, hey, do you plan to vote? Do you plan to vote? Do you plan to vote? And then I'm going to do that legit 300 times. Okay, so in each case, I'm going to have 300 p hats.
Could you explain? I don't quite understand what you're saying. So you say you're gonna call 10 people and you're gonna do it 300 times?
That is correct. And so every time I call 10 people, I'm going to compute the sample proportion that say they're going to vote in the upcoming election. And then the next 10 people I call, I'm going to compute a new p hat. And then for the next 10 people, I'm going to compute a new one and a new one and a new one. Okay. And
So
then
would you be calling like 3,000 people in all? Is that what you're saying?
yes, but every group of 10 is different. Okay.
Okay.
Yes, but I am calling 3,000 people in total.
All right.
Okay. But every group of 10 is different. Okay. And then I'm going to do the same thing for 50. Okay. And then I'm going to do the same thing for 100. Okay.
Okay. All right. Thank you.
So here's what I want to do. I want to show you the histogram of what each of these 300 p hats will look like. Okay. So let me show you. Is everybody okay if I go to the next slide?
I'm still copying. Can you please wait a minute?
I do not mind waiting one bit. You know, it's funny, just as a little sidebar, when I was on mute, my kid started crying. So he's alive today. You guys just missed it so far. I probably jinxed it for the second half of class, but we'll see. All right. Let me know when I can move on to the next slide.
You can move.
Thanks.
Thanks for waiting.
Yeah, no problem. Okay, so this is it. This is 300 different p hats, okay? So this is 300 p hats of sample size 10. Okay. What does this somewhat look like? But it's not perfect. Looks close to a bell curve, right? Is it perfect though? Does it look exactly like a bell curve? Yeah, like you notice it because that looks a little skewed, right? Like it's somewhat, but it's not great. Okay, it's definitely not great. But if you were to take the average of all the different p hats, okay, so just so we're clear what I mean, like suppose sample 1, it came back as 4 out of 10 people. Like this is where the first p hat would be. And then if sample 2 came back at 5 out of 10, it would be right there, and so on. So what you're doing is you're constructing a histogram of legit 300 different p hats. Well, if you were to take the average of all your p hats, what is the average really close to? It's close to what I said the real population proportion would be. Okay, that it was really 0.42. So the mean is close to it, okay? And then if you were to calculate the standard deviation of all these, you would get 0.16, okay? So now let me show you next what it would look like instead of the 10 people, I called 50 people in each sample. You okay if I move on? Okay, good. So this is what it looks like with 50 people, okay? So now the 300 samples are of 50 people each. Okay, well, look, the mean is still really close. To 0.42. And notice when I increased the sample size, the standard deviation got smaller. So it was at 0.16, now it's 0.072. So increasing the sample size lowers the standard deviation. So does this look kind of like a bell curve? It has a little dip in the middle, but does it look a little bit better? Yeah, it's like almost looks more normal, but not exactly normal. Okay, but not perfect yet. So I'm going to go to the next slide if that's okay. So let me show you the sample size 100. It's like, wow. Okay. So now, oh, you know what? Sorry. I just like, it's been a long couple days. All right. You know, I think I told you guys this. My wife works in politics. So it's been like nonstop for like the last 2 weeks. It's just crazy. Yeah. I feel bad for her today. A lot of like media interviews and stuff. It's just been a rough day. Anyways, so this right here, notice what happens here. So this is 300 p hats of sample size 100. Notice what the mean of this distribution is, okay? So the mean is 0.42, okay, which is the same as the population proportion. Okay, so the average of all these sample proportions was actually the real population proportion. Notice the standard deviation as you increase the sample size continues to get smaller. And what does this curve look like now? How would you describe this shape right here? You guys see in the bell curve shaped? What do you guys think? Yeah. So this curve now looks normally distributed. Okay. So it seems that like once you, this is what I'm kind of hinting at. P hat is just like X bar, okay? In the sense that it's sampling distributions. If you look at enough different P hats, it'll be normally distributed, okay? But in this case, it's like once you hit a certain sample size, the sampling distribution of P hat will follow this bell curve, okay? And it looks like it didn't do it when it was 10. It didn't do it when it was 50. You know, once we got 100, it really started to look that way. So there's going to be a number check for this. I'm going to show you in the coming slides. Okay, so what I'm saying here, just so we're clear, is the sampling distribution of the sample proportion which is that p hat, looks normally distributed. Okay. Everybody okay if I go to the next slide? Okay. So look, here are the key points that we're seeing from this. Okay. As the sample size n increases, the shape of the distribution of that sample portion becomes approximately normal. Okay. As we went from 10 to 50 to 100, it went like this. Yeah, kind of, yeah, a little bit better. Yeah, I see the normal curve. Okay. The mean of the sampling distribution of the sample proportion equals the population proportion. So the center of this distribution here should be is centered around the real population proportion. So what this means is like when you take enough sample proportions, like sometimes the proportions will be really high than the real value. Sometimes it'll be really low, but on average, the proportion should be the real value. And then the standard deviation of the sampling distribution here of this sample proportion decreases as the sample size increases, right? So like what this is saying is as you sample more and more individuals, your estimates get better and better and better and better and better. Okay. So now what we're able to say is give me some formulas for the mean and the standard deviation. Like you can see them right here on the bottom. Okay, but what are some formulas for them now? And so this will be the most important slide from this section. Like we're going to use this slide right here in every single one of these problems. Okay. Okay, so we'll use in every example. All right, so there is a number check to guarantee that the shape of the sampling distribution of p hat will be normal. So, and I'll do an example where I walk through this. Okay, so the shape of the sampling distribution of p hat is approximately normal as long as this number check works out. You take the sample size, you multiply it by whatever the population proportion is. You multiply that by 1 minus whatever the population proportion is. And as long as this is greater than or equal to 10, okay, it's going to check out and you'll say, hey, guess what? My p hats will be normally distributed. Okay. And when something is normally distributed, okay, you have to say what the mean and what the standard deviation is. Okay. So the mean of this sampling distribution of p hat, we denote now as mu sub p hat. So the average of the sample proportions, and that should be equal to the population proportion. Okay, that's the most important one right there. This is the mean. And the standard deviation is just given by this formula, sigma p hat. And it's just the square root of p times 1 minus p divided by n. And this is our standard deviation. Okay. I know it's a lot, like how many people just out of curiosity like in the chat are being like, wow, this is just a lot of symbols and I'm not sure how we're going to use this. Yep. But like, did you notice, and it's okay. A lot of times that is the way with math, right? But like, did you notice like when we did the sampling distribution of the X bar, after I did one example, it was kind of like, oh, okay. Yep. I can do this. I got this. It's going to be the same with this, you know. Have you guys noticed that that's kind of like the trend of this class? When I introduce the theory, it's like, what's going on? And then, all right, let me see it in practice. Then it'll be the same way with this, okay? So stick with me, I understand. All right, is everybody okay if I Move to the next slide. Okay. No, not yet. No problem. No problem. That's why I ask. All right, what do you think, Liliana? Okay. Awesome. All right, so don't worry about this next part for a check, but just realize the model on the previous slide requires sample values to be independent. So what this means, if like you have a finite or really small population, you never want to sample more than 5% of it because then your samples are not independent anymore. And then regardless of if the number checks out, the mean will always be P and the standard deviation will always be this formula. But I will give you a hint, all right? I'll give you a tip. Every problem I give you in this class, the number check will always work out, okay? So in this class, this will always check out. Okay, so you'll see me in action when I do this, okay? So I just want to get through the first couple parts of one example, okay? So you can see how this will be used. All right, one example and then we'll call it quits for today. Sound okay, guys? Sound okay, everybody? Ugh. Yep. It's going to be an interesting weekend, so we'll get there. All right, so here's the first problem. The United States Census Bureau reports that 27% of the population has obtained a bachelor's degree or higher, okay? Is anybody surprised by that number, just out of curiosity? Like too low, too high? Think it's too low or too high? It's low? You know what's interesting? So this is a statistic from everybody, right? Regardless of age. So like, you know, if you look at previous generations, having a college degree wasn't always necessary for success in life, right? Like, or financial success, I guess is the way to say that. Forgive me for misspeaking, but like, if you actually look at the younger generation, like your generation and even my generation, a much larger proportion does have a college degree, but this is just adults in general, okay? So now does that kind of make sense why it's that low? Yeah, okay. So suppose a random sample of 200 adults is obtained, okay? So for these problems, okay, I'm gonna give you some type of proportion. Okay, so I'm giving you P, and then I'm gonna give you some sample size, okay? So you're given P is equal to 0.27 and N is equal to 200, okay? That's legit all I'm ever gonna give you for these problems, okay? Like in the start, okay? So just two numbers, and then we're gonna work a whole bunch of different stuff. So the first thing says, describe the sampling distribution of P hat, the sample proportion of adults who have a college degree. Okay, so first off, our variable here, okay? What is P hat? Well, P hat is the proportion or the sample proportion of adults in a sample of 200 who have a college degree. So I'm going to give you another hint. Like what we basically want to show is, or say, is that it's normally distributed. And then I want to give the mean and standard deviation. Okay. So if you look back at this slide here, there's a number check. Okay. And the number check is just n times p times 1 minus p has to be greater than or equal to 10. Well, look up here. You're given n and p. Okay, so let's just take these numbers and plug it in. N is 200. P is 0.27. And then it's 1 minus 0.27. And let's just verify that that's greater than or equal to 10. So 200 times 0.27 times 1 minus 0.27. I'm just curious, did anybody follow along and get that number? I got one yes. Yep, one yes, yeah. All right, thanks everyone. 39.42. Okay, do you notice how 39.42 is greater than 10 here? So what I'm saying is the number checks out. Okay, so this checks out. So here's what we can now say, okay, because this number checks out. Thus, the sampling distribution of this p hat, okay, this p hat that we just have over here, is normally distributed with, okay, mean. If you look back on this slide here, remember, well, I gotta go back one more. Remember I said this is like the most important slide? Mean we denote as mu sub p hat, and it's equal to p. So the average of these sample proportions, it better be equal to the population proportion, which is 0.27. And the standard deviation, which is sigma p hat, we just have to use this crazy formula here. The square root of p times 1 minus p divided by n. Which is the square root of 0.27 times 1 minus 0.27 all over the 200 people we called. So this you just have to plug into your calculator, right? So second function square root 0.27 times, then in parentheses 1 minus 0.27, close that set of parentheses, divided by 200, close the final set of parentheses on the TI-83, and you should get this, okay? And this is important. You have to take this out 4 decimal places. You have to, okay? Just out of curiosity, did anybody get this value when they did it in their calculator? Okay, I got one yes, perfect. I'll be honest with you, like after you see a few examples of this, you'll see the pattern to how this is solved. And like the most common error I see with students is that they somehow calculate this wrong. So just make sure that you can practice this and it works out. So it's 0.0314 when I round it. Okay. So look, normally distributed mean standard deviation. I'm just going to ask you a probability question now. Are you guys ready if I go to the next slide?
Yes.
Thank you. All right, so in a random sample of 200 adults, what is the probability that less than 25% have a college degree? Okay. So I want to now ask, if I'm going to call 200 adults, what's the probability that my p hat here is less than 25%? So you have to change this to a decimal here. So it's like, well, how the heck are we going to even answer this, right? Well, here's exactly how. Normally, mean, standard deviation, piece of cake. What I'm going to do is I'm going to sketch the distribution of p hat. And just in the chat, how did I say p hat was distributed? Normally distributed. Look, boom, right there. So it's going to follow this bell curve. It should be centered at the population mean, which is 0.27. And I want to be less than 0.25. So I'm going to shade to the left. What's the best way to solve this now? Starts with a C, ends in calculator. Thank you for the laugh there. Yeah, you know what you can use? You can just use your normal CDF here. So it's a left-tailed test, so my lower is minus 9999. My upper is 0.25. What always goes next here? Is it the mean? Yeah. And like, look, that's why we have the mean right here. It's 0.27. And then next is the standard deviation, which was why we found it right here, 0.0314. So I'll do this one in the TI-84. I haven't done that in a while. So second function distribution, normal CDF, minus 9999, 0.25, 0.27, 0.0314. And when you plug this into your calculator, you get this, 0.2621 when I round it. So let me ask you this, was at least using the calculator not too bad? Okay, is it just like, what I think is the hardest thing is just like, is this a mean? Is this a proportion? What number? What formula do I use? Like, I tend to think that's the hardest thing. Would you all agree? Yeah. All right, let me just do this last one here, and then we'll call it quits for today. And we'll pick up here next time. So in a random sample of 200 adults, what's the probability that more than 30% have a college degree? So it's the probability that your p hat is more than 0.30. So it's normally distributed. So I want to be greater than 0.30. So it's just going to be normal CDF. Here, this is my lower now. My upper, because it's a right tail test, is 99999. The mean and standard deviation stay the same. So I'll do this in the TI-83. So second function distribution, normal CDF, 0.30, comma 9999, comma 0.27, comma 0.0314. And you should get 0.1697. All right. Felt like you're probably drinking from a fire hose today. But at least was using the calculator not too bad today.
Yeah, it wasn't so bad.
All right. I'm going to pick up here next class. We'll do another example or two of each of these, okay? So that you'll get more and more practice with this. And then next class, I'll also post your next homework so that you can get ready for the next exam. I'm going to try to get it done Friday. I'm going to try to get the homework graded by Friday. Forgive me if I take the weekend though, okay? But I'll try for Friday. And I'll shoot you all an email when it's graded. All right, everybody, any other final last questions before I say goodbye and we all have a good weekend? All right. Okay, all right, everybody. Yes, the test got moved to the 17th. So I'm not having the test on the 12th. We're gonna have it on the 17th. So the reason to do that is next class, the 10th, we'll finish up this stuff and then it'll give you a week to prep for it. Okay? Yep. All right. Okay, everybody, have a good good day and I'll see you next week.